All right, section 6.1 is exponential growth and decay functions. An exponential function has the form y is equal to a times b raised to the x power, where a cannot equal 0 and b is a positive real number other than 1. So if a is greater than 0 and b is greater than 1, then we'll have growth, and b is known as the growth factor. If a is less than 0, and b is between 0 and 1, we'll have decay, and that will make b be the decay factor. So example 1, tell whether the function represents exponential growth or exponential decay, then graph the function. So again, if we look at it here, the 1/3 now is our b. We should understood that there's our a is 1 in this case. So since b is between 0 and 1, we'll have decay. Okay, so now what we'll do is let's go ahead and make a t-table here again. And I went ahead and made the graph earlier here for you. So I'm going to use -2, -1, 0, 1, and 2. And when I take 1/3, I'll just put the first one here to show you. If I take 1/3 raised to the -2 power, remember I can write that as 1 to the -2 and 3 to the -2. But remember, since they're negative, I'm going to flip them. So now the 3 will come up on top and it'll become positive. And on the bottom, we'll have 1 squared. So we'll know that that is 9. All right, so we would do the same thing for -1, which would give us 3. Anything raised to the 0 power is 1. And then at 1/3 raised to the first power is 1/3. And 1/3 raised to the second power is 1/9. All right, so if we graph that at -2, we're at 9. At 1, we're at 1, 2, 3. Anything raised to the 0 power is 1. Should always go through there. And then we'll have like 1/3, and then we'll have 1/9. So now what's going to happen here is if I draw my curve there, what we should see is that it'll follow the x-axis, but it will never cross it right now. Okay, when we do our shift laws from later on, it might do it, but according to this, it won't, because the x-axis is an asymptote. And if you recall from probably regular algebra 1, what we know about an asymptote is it gets close to but will never cross. In this case, the x-axis. Again, remember, when we do our shift laws, that can change for us, okay? So now some real life quantities increase or decrease by a fixed percent each year or at some other time period. So the way that we see that is we'll have, y is equal to a, which is our initial amount, again. Okay, times 1 plus or minus r raised to the t power. So our t is going to be our time period. And our r is our rate. which is going to be our percent increase or decrease. Okay, increase or decrease. The whole thing, the one plus or minus R, is going to be our growth or decay factor. Okay, that again includes the one plus or minus, because if it's one plus, it's going to be greater than one. If it's one minus, it's going to be less than one. So again, that just from what we talked about up above, that'll tell us if it's a decay or a growth. So example 2, the value of a car Y in thousands of dollars can be approximated by the model Y is equal to 32 times 0.92 raised to the T power, where T is the number of years since the car was new. So A, is it going to be exponential growth or decay? So again, we're going to look at our B here, which is 0.92. We know that 0.92 or 92 hundredths is between 0 and 1. So we know we're going to have decay. Okay. Now it says to identify the percent decrease. So remember, what we're doing here is we're going to take our 1 plus or minus R, and we're going to talk about that. Well, so if we look at here, here's our 1 plus or minus R. So we're going to say that 1, in this case, it's minus R because we know it's less than 1, is going to equal to 0.92. Okay? So now if I subtract 1, and I'll go ahead and work it out the whole way for you, that will give us negative R is equal to negative 0.08. So again, if we multiplied both sides by negative 1, we would get a positive R of 0.08. And that's in decimal, so we have to change it to percent. So that would equal 8%. Okay, and then estimate when the value of the car will be 9,600. So look at, put the equation in calculator. All right, which I've already done for you. So I'm going to show you. So if I look here, I did plug it in. Notice I have y is equal to 3.2 times 32 times 0.92 raised to the x power. I can put x, I can put t. Since we don't have a t on the calculator there, I'm just going to use x. All right, so again, our x would be our x-axis. And so what you have to do now is you might have to zoom in or out, but again, you can kind of look. So I'm going to zoom out a little more for you. So if I click right here, we should see that our point is at 32, all right? Because again, if x was 0, anything raised to the 0 power is 1, so 1 times 32. So that should make sense. So with this calculator, what you basically have to do is you just have to hold on to it and just keep following it, okay, until you see, what did we say, 9,600. So that would be 9.6, all right? So if we look here, 9.6, it looks like it's around 14.4. So we could go ahead and say approximately T will be approximately 14 years. So again, look and see what the Big Ideas platform wants you to round it to, okay? Make sure you remember that, okay? Another example, in the year 2000, the population of a city was 1.04 million. During the next 14 years, the population increases by about 2.05% each year. Write an exponential growth model, then estimate its population in 2008. So our exponential growth model is y is equal to a times b raised to the x power. Okay? We're told our initial amount was 1.04 million. So let's just go ahead and put 1.04, and then we're going to find out what the million is. Okay? And then we know that it is increasing. So we're going to have 1 plus, and we're going to take our 2.05%, and that's a percent. So we're going to change that to a decimal. So over here, 2.05%. I'm going to go 1, 2, put our decimal there. So we're going to have 0.0205 that we're going to add to our 1. And again, since we're going to be putting it in the calculator, we're going to go ahead and put an x there. Okay? So we'll have y is equal to 1.04. And we're going to have 1.0205. And again, from 2000 to 2008, that tells us that our x is going to equal 8 years. And when I plug that into the calculator, just exactly like I have it right there, you should get approximately 1.22, and that will tell you it's million. Okay? And then it asks, estimate the year when the city's population was 1.3 million. So again, we're going to go to our calculator and we're going to trace it, which means I'm just going to move it until I see where it's close to 1.3 million. All right, so I did do that on another one here for you. So I have 1.04, 1.205 raised to the x power. Again, if we look right there, okay, there's our 0 is 1.04, which again is what we would expect. And notice this time it is going up, so it is increasing. If we remember, I can put it right here real quick. The last one, it was decreasing. So notice that we are doing the same kind of thing. And if I zoomed in or out, you would see it still has the same kind of shape. It starts out slow and then it goes fast. Or if it's decay, it's going down fast and then starts evening out. Okay, so again, if I just trace here, again, I'm just going to keep going up. And as you can see, I know, I just had it there. See there where it says 11, and it's exactly at 1.3. You might have to estimate it, but on this one here, it worked out nice. So we were given that x is equal to 11. So again, we're going to take that, and that we will add that to the year 2000. And that will tell us that the population at 1.3 million was in 2011. Okay? Oh, sorry. But I put it right there for you. Okay. A couple more examples here for you. So example 4, the amount Y in grams of a radioactive isotope barium-140 remaining after T days is Y is equal to A times 0.5 raised to the T divided by 13. That is T divided by 13, people, where A is the initial amount in grams. What percent of the barium decays each day? So on this one here, remember, percent is the same as your rate. So that's what we're going to have to find out. So we can write this as y is equal to a times 0.5 raised to the, again, I'll write it for you here, t divided by 13. So now remember on this, we're going to use something that we just did in our last chapter. Remember that 13, I can rewrite that as a, because right now we're just wondering about the rate. The initial amount isn't going to mean anything to us right now. I'm going to say 0.5. And notice what I'm going to do here. I'm going to put 1 over 13. And then I'm going to put our t outside. Because now remember, when I have it like this, I can remember from last chapter that 0.5 raised to the 1/13th power is, since it's 1 over 13, that's the 13th root of 0.5. And that will equal 0.9482. Okay? And this is R 1 plus or minus R. So again, this is our 1 plus or minus R is 0.9482. That means that it was subtracted from 1. So just like I did above, I'm going to take 1 minus R is equal to 0.9482. And on these ones, you go to the 4 decimal places there. I think it'll make it easier for you. So then we're going to say negative R is equal to 0.9482 minus 1, or negative R is equal to negative 0.0518. Our regular R is equal to 0.0518. And again, we want to change that one to a percent since it is a decimal. So I'm going to move it this way to get my percent. And that will tell us then that R is equal to 5.18%. Okay, and the last thing we're going to talk about is compound interest. This is very a good question here on when you're saving money. So compound interest is interest paid on the initial investment, or that's your initial amount. But in this, we'll call it the principal, and on previously earned interest. Interest earned is often expressed as an annual percent, but the interest is usually compounded more than once per year. This is given by the formula A, which is our amount that we'll have in the bank, is equal to our principal, our initial amount, times 1 plus, because again, it's money, you want it to grow, 1 plus the R, which is again our rate, divided by N, and then it's going to be raised to the N times T power. So on here, okay, N is equal to the number of times compounded per year. Okay, so if it's semi-annually, that would be 2, so our N would equal 2. If it was quarterly, it would be 4. If it was monthly, it would be 12, and so on and so on. We're going to talk about that a little more tomorrow, I believe. Okay, so our last example, you would deposit $8,600 into an account that pays 1.32% annual interest. Find the balance after 4 years. Okay, that's our T, where the interest is compounded quarterly So this would be our N, and our N is equal to 4 times. All right, so we're going to take our amount is equal to our initial investment was $8,600. Okay, and then we're going to take 1 plus our rate is 1.32%, so 1.32%. If I want to change it to a decimal, I'm going to go to this way. So we're going to have 0.0132, and that's going to be divided by 4. That's our N. And then we're going to have our N, which is 4, and then our T, which in this case was 4 years. All right, so now you should be able to plug it in exactly like you see it right there, ladies and gentlemen, in your calculator, and you should get $9,065.49. So if you think about it, your money improved by almost what? $100 a year almost. So think about something like that when people give you money for your graduation. All right. Have a nice day, ladies and gentlemen. I'm done.